Welcome to the Water Resources Podcast. I'm Bridget Scanlon, and in this podcast, we discuss water challenges with leading experts. And today I'm pleased to welcome Mohammad Shamsudduha, better known as Shams, who is a professor at the Institute for Risk and Disaster Reduction at the University College of London. Welcome, Shams.
Thank you very much, Bridget, for having me on your podcast show. It's my pleasure to be here with you. Thank you very much again.
And Shams, maybe you can tell us a little bit about the institute where you're working. I mean, it seems like a lot of times these days we're talking about disasters and how we can adapt to these things. And you mentioned that this institute was originally a cross-disciplinary program at University College London and then developed into its own department. So it emphasizes the importance of managing these risks.
Yes, yeah, thank you. Yes, I work at Institute for Risk and Disaster Reduction. We call it IRDR for short. It's an institute that was established in 2010. The idea was that this very much interdisciplinary institute would lead research as well as education cross discipline and across the campus. So that was the kind of original idea when this institute was developed. And over the last 10 years or so, we have really grown exponentially, and we became a fully fledged department in 2020 when we actually launched our BSc program in Global Humanitarian Studies, which I have been leading for the last 2 years. So it's quite an exciting place to be because my colleagues are from various different disciplines. So I have colleagues who are experts in development economics and experts also in international migration laws. And I have colleagues who are covering international relations and gender intersectionality and everything, like all of these different disciplines come together by a common thread, which is disasters that are caused either by naturally occurring hazards or anthropogenic hazards. So we look at disasters through many different lenses, and I think I find it quite exciting to be part of this interdisciplinary department. Although by background I'm a hydrogeologist, I did my PhD also at ECL some time ago, but I find it quite fascinating to be part of it.
Well, I think that's amazing because oftentimes we focus on the physical aspects of problems, being natural scientists, but oftentimes it's people behavior or things like that that are maybe more important in how they adapt to different disasters and how they can manage them. You recently published a paper in Science titled The Bengal Water Machine, which is very exciting. And you got the cover of Science also, which is amazing. And Shams, you're originally from Bangladesh. And this paper then talks about how groundwater pumpage for irrigation has made space for increased recharge from monsoon rains and how it can maybe manage the extremes that you see annually in Bangladesh, either dry seasons or flooding during the monsoons. And maybe you can describe this work a little bit, and congratulations on getting it published in Science.
Thank you very much, Bridget, for your kind words. Yes, it is an exciting piece of science that we got it published in Science back in September last year, and it was accepted, and that also kind of triggered discussion not only within the academic or research environment, but also it it created a lively discussion on social media. So the member of public, particularly in Bangladesh, they were quite excited and interested to know about this discovery, if you like, of the Bengal Water Machine. So it's quite a fascinating piece of work. And over the last, 6 months or so, I have still been communicating with people who are interested in that work, um, and I spoke with a number of different people from Bangladesh who come from quite a different background and discipline. So for them, it's a kind of foreign idea that, by pumping more groundwater, you are increasing the storage. How come? So we know this is the opposite. When you pump more water, of course, you are going to deplete. So I find it quite interesting also when I communicate that to the member of public. Um, a little bit about the background to this work. So um, nearly 10 years ago or so, when I was kind of finishing up, or actually I finished my PhD more than 10 years ago. So towards the end of my PhD work, when I was working on the long-term groundwater level records from Bangladesh that are monitored by the Bangladesh Water Development Board. So it's the national agency who is in charge of the monitoring infrastructure of water resources in Bangladesh. I actually noticed that number of hydrographs that I looked at very carefully showing increased seasonality over time, where the wet season water levels were coming back to the kind of background level after the monsoon because of the recharge. But then the dry season water levels were going down incrementally over time. And this got me thinking, and also my supervisor, Richard Taylor, from geography, UCL. So we were quite fascinated to see these hydrographs. We had some limited evidence when we did the study more than 10 years ago. So we did eventually publish a paper in Hydrogeology Journal where we described this phenomenon being induced groundwater recharge because of pumping. So since then, I always had in mind that we have to do something about it. We have to do a national scale, a very thorough analysis using this wealth of groundwater level records from the Bangladesh Water Development Board. So then the COVID came 2 years ago, and we were all in lockdown situation. So I thought, okay, how can I keep myself engaged in research and not worrying about the COVID pandemic so much? So I spend a fair amount of time sitting on my computer at home, looking through 465 long-term hydrograph records, and we identified about about a one-third of them, um, of these long-term hydrographs, were actually showing uh, the signal that the dry season water level was going down over time, but then uh, there was recovery, if not to the full background level at the end of the monsoon, but there was recovery happening at the same time. And um, this incremental increase in the kind of seasonal oscillations over time suggested that groundwater recharge was induced through pumping. And we mapped out at the national scale using this 465 monitoring records, and we came up with an estimate that about 75 to about 90 cubic kilometer of fresh water captured in this process that contributed to the groundwater storage over a period of kind of 30 years or so. So it's a huge amount of freshwater storage that was captured because of pumping by farmers who didn't actually know that they were creating this big water machine, if you like, in the subsurface environment. So I'll stop here and see if
Yeah.
we have any comments or reflection.
Right. Well, that is a huge amount of water, 75 to 90 cubic kilometers. And in the US, we oftentimes talk about million acre feet. So 1.2 cubic kilometers is 1 million acre feet. So it's similar volume of million acre feet. And it's as big as the Three Gorges dam storage. You know,
That's correct.
and we
Yeah.
just don't think about those sorts of things. So I guess summarizing the basic idea then is when they started pumping more and more groundwater, the groundwater levels were dropping, and so seasonally then you had more storage to increase recharge from the monsoon and from surface water. And then by that, then the irrigation from groundwater, you were increasing food security and other things. So this concept was introduced in the mid-70s also with an article in Science called the Ganges Water Machine. Maybe you can describe a little bit about how the Bengal Water Machine kind of differs, or, you know, how it relates to the original concept, and if there was much work done with the Ganges Water Machine.
Yes, interesting. Yes, of course, we were quite inspired, if you like, by the original paper by Roger Revel and Venkatachalya Lakshminarayana back in 1975 that was published as the Ganges Water Machine in Science. And uh, in many ways, it's quite similar to the Bengal Water Machine, but there are some significant kind of differences, the variations between the two processes described in these two science articles. So in the original paper, the 1975 Ganges Water Machine paper, of course, Revel and Lakshminarayana, they proposed an idea. So it was a kind of concept that, well, there is a lot of water during the monsoon season in the northern part of India, so the Ganges floodplain, the Ganges river basin. And also, this is the region that suffers from seasonal flooding. And at the same time, if you look at the map of population of the world, you will see the concentration, the density of population is one of the highest in the world for this part of India and as well as Bangladesh. So they thought, well, you know, food security is a big problem. So they proposed an idea that, okay, if the farmers uh, install their pumping wells along um, the Ganges River and their distributaries, and they pump water for irrigation during the dry season, and if they increase incrementally every year, pumping more and more groundwater for irrigation, then that's a depleted aquifer. So the space that is created through pumping can be replenished from the monsoon water, because there is plenty of water during the monsoon season that should be able to um, replenish the depleted groundwater system. And that would be a win-win situation, because that will reduce the flooding during the monsoon season. But at the same time, it will address the food security issues of that region that is highly populated. But that was an idea, and they used some um, analytical groundwater models to test the viability of the concept, and they showed mathematically that it is possible uh, to achieve that. But that was it. Um, there was no kind of
Field
policy
testing or anything, yeah.
or field testing, no initiative by the government of India or Bangladesh, or even the people of the farmers. So that idea was there, published, and then there was no practice, no field testing. So when we had the data for Bangladesh, and it's long-term data, because some of the records we looked at go back to 60s, mid 60s and early 70s, when there wasn't groundwater-fed irrigation in Bangladesh. So we could look at a situation from nil pumping, no groundwater pumping, to very intense development of groundwater. through a number of very long-term record. And it's the story that we are telling through this observational data that actually happened in the past. So over the last 30, 40 years, farmers, around 16 million farmers in Bangladesh, they created this subsurface invisible water machine through kind of collective action that was not coordinated or facilitated or promoted by the government or farmers association or anyone. So it just happened, and then this is what we reported from the observation data. So going back to your question, the differences between the two is that one was an idea that was proposed in the Ganges water machine, but then in the Bengal water machine, through observation, we um, we demonstrated the operation of such machine at the large basin scale, and that in terms of groundwater replenishment, uh, we have observed that groundwater replenishment comes from not only from the drainage networks, but also through diffuse groundwater recharge. So it's a combination of various recharge pathways leading to this augmented groundwater recharge through this Bengal water machine. Now, I must admit that we only looked at 465 good long-term records, and we have seen in one third, 156 of them showing some kind of indication of enhanced groundwater recharge. About a third of the rest of the 465, we have seen consistent and long-term depletion taking place. So we are not ignoring the fact that some areas of the country, such as Dhaka city, which is a home to more than 20 million people, heavily dependent on groundwater system for public as well as industrial water supply, do suffer from depletion. And there may be some enhanced recharges going on, but then the withdrawal is so much more that the balance is negative. So I just wanted to make sure that your audience should know that we are not telling a very rosy story of groundwater development across Bangladesh.
But I mean, it's very interesting. I mean, maybe the Ganges water machine emphasized, groundwater pumping near the rivers, but what you're actually seeing in many regions is that even far away from the rivers, you're benefiting from this increased storage capacity and increased recharge from the widespread flooding from monsoon. And, it reminds me a little bit about what's happening in the Mississippi, if we think, because they're pumping more groundwater in the Mississippi alluvial basin than they are in the Central Valley. But because it's a humid region, with much more surface water, they're probably inducing recharge from surface water and capturing surface water that Lenny Conoco documents. And
Right.
the other aspect of this work is that, when you talk about creating this space underground, Lenny Conoco has suggested that depleted aquifers in the US have a space of about 1,000 cubic kilometers, which is greater than the surface reservoir capacity. And so we need to think about these things, even though they're invisible, and we need to use them more actively. So I think that's fascinating. It's nothing managed. We talk about managed aquifer recharge, but here you're describing something that happened and unintended consequences, which were positive. Also, another aspect of your work, which I think is very important, is the linkage between the areas where you see this Bengal water machine operating and the geology. The soils and where you can get that increased recharge. Maybe you can describe a little bit. You're seeing it more in the west and north part and not in other regions where the soils are lower permeability.
Yes, I think the geology is a critical part of the equation. So there are three factors involved. So of course there has to be pumping, an area that is actively pumped. and then that has to be an area that receives a lot of monsoon rainfall. And the third thing is the geology, which is very important. So we have seen this water machine to be operating very well in the north central and northwest part of Bangladesh, where the geology is it's mostly alluvial system, unconsolidated sand, silt, and clay um, uh, that form the aquifer system in that region. But if further south, if you come to the kind of coastal deltaic environment, you tend to see a lot more heterogeneity in the subsurface environment, a lot more layering, and the aquifers there are much more kind of fine grained, composed of fine grained silt and sand rather than medium to coarse grain sandy aquifer that we normally see in the northwest and the northern part of Bangladesh. So there is a spatial variability in the observations that we observe.
So, I mean, with this improved understanding then of how the system works, then they'll probably be able to manage it better and maybe even encourage or incentivize some of these types of practices. So that's great. I think another aspect of your work, Shams, that I really admire is that you not only look at water quantity issues, but in much of your research also you have emphasized water quality aspects. And your early work on arsenic in Bangladesh, maybe you can describe some of that work.
Yes, yeah. Thank you, Bridget, for the question on groundwater arsenic contamination in Bangladesh. Yes, it is a huge uh, problem, environmental problem, and it's a huge public health concern in Bangladesh because the naturally occurring arsenic contamination of shallow groundwater in Bangladesh was discovered in the mid 90s. And I was involved in a number of research looking at arsenic contamination of shallow groundwater. In fact, my very first research was on arsenic contamination in Bangladesh, and it's naturally occurring, and um, it covers a wide most part of Bangladesh, almost 2/3 of Bangladesh. You can see the shallow groundwater. When I say shallow, it's less than 150 meters below ground. Often it's very shallow, so we are talking about 30, 40, 50 meters depth of aquifer that are highly contaminated with arsenic. And it's a problem, particularly in the south, central, and the whole, pretty much the southern deltaic environment is pretty much contaminated with this heavy concentration of arsenic. And we are talking about a concentration that is several order of magnitude than the 10 micrograms per liter of WHO standard, or even 50 micrograms per liter, which is the Bangladesh national drinking water standard for arsenic. We have seen arsenic in the order of 1,500 to nearly 2,000 micrograms per liter. So it's very, very high concentration of arsenic in shallow groundwater.
And how did this, there was a shift. I know in India, there was concern because of all of the microbial contamination from surface water. And so then they thought they would shift to groundwater and avoid some of that issue and the mortality related to diarrhea caused by microbial contamination. And then, however, then after a while, then they realized that the arsenic in the groundwater was creating a big issue also. So maybe you can describe the history of this in Bangladesh and how they discovered the issue and how they're dealing with it.
Yes, you have already alluded to it. It's actually the case, similar to what happened in India, is also a similar case that happened in Bangladesh. So the mortality from diarrheal diseases, particularly among under 5 age children, was very high. in these 80s, early 90s, when people were using contaminated surface water for drinking and domestic water purposes. So um, by by the early 80s, we already knew that there was plenty of groundwater available in the country because groundwater was first developed for food production in the northwest of the country. So then the development started um, to provide a public water supply from groundwater. And as you know, Bangladesh it has plenty of groundwater. We have alluvial aquifers everywhere, pretty much throughout the country. And you can have your own tube well in the backyard, just maybe 10, 15 meters below ground. And it's not very very expensive to install a hand pump in your backyard. So people started to copy each other, and of course government and donors and other NGOs work together to provide drinking water supply from groundwater. So that happened pretty much throughout the 80s, late 80s, early 90s. Um, and then we didn't actually know that arsenic was present at such high concentration in groundwater until 1993, when we first discovered high concentration of arsenic in groundwater, because people were presenting with skin blackening of their palm and feet. So the skin lesions that were associated with the buildup of arsenic in their body was a wake-up call, really. I mean, they were presenting that to the doctors, and then eventually the investigation led to the discovery of high arsenic concentration that was coming from basically groundwater. So in terms of the shift from surface water to groundwater, we had positive side of it because the mortality from diarrheal diseases has dramatically decreased over time. I can't tell you the figures on top of my mind, but the figures are suggesting that there is substantial improvement in that. But then again, millions of people were exposed to dangerous levels of arsenic concentration through contaminated groundwater drinking.
Right. I guess people have termed that the greatest mass poisoning, but it's naturally occurring. And so the arsenic is ubiquitous, really, but then it can get mobilized or people can start using it. And so most of it was sorbed into iron oxides, and then it gets mobilized, and then you can get it in your drinking water. And so basically you were trading off microbial contamination for arsenic contamination. But
That's
not all groundwater in Bangladesh has high arsenic levels. Maybe you can describe that a little bit.
Yeah. There is also there is a very clear kind of special pattern to the geographic distribution of arsenic. So British Geological Survey and Bangladesh Department of Public Health Engineering, they did a long national scale big campaign of sampling more than 3,500 hand pumps for arsenic testing. And from that data set, we can see, we can work out the spatial distribution of arsenic. And as I said, it's mostly concentrated in the south central part of the delta, but there are other areas where you can find arsenic. One of the issues is that arsenic can actually vary spatially within a very short distance. So two tube wells 100 meter apart can have very different concentration of arsenic. So there is that short term, not short term, I mean short spatial variability, very high. But at the same time, you can see at the large national scale that there are some clear structures to it. So connecting that to the Bengal Water Machine, you might be wondering, well, if you are, pumping groundwater and then you are abstracting too much water, and maybe your, deep groundwater might get arsenic from the shallow groundwater. So there is that concern there. But fortunately, in the northern part and in the northwestern part of the country, where the Bengal Water Machine has been operating very well, and we have seen increased or enhanced groundwater recharge, are the areas where arsenic concentrations are actually very low. Often it's less than 50 micrograms per liter, which is the Bangladesh standard. So there is that um, um,
Right.
what's the word? Yeah, so there is that less concern, I think, in terms of arsenic concentration
But
going
also,
into the.
you mentioned, Shams, this vertical stratification. So where you have arsenic contamination is oftentimes in the shallow zone, maybe 30, 40 meters. But then the deeper system then has usually got low arsenic. And so with increased pumping of the deeper system, then there would be concern that you would induce arsenic groundwater into that system and contaminate it. But I think some of your studies suggest that if you limit deep groundwater pumpage to domestic uses and not irrigation or other large-scale uses, then that you can protect that deep groundwater, and you can possibly provide arsenic low groundwater for the next 100 years for domestic.
You're absolutely, yes, you're absolutely correct. There is that concern that over time, because of heavy pumping of the deeper system, perhaps the deep groundwater, which is relatively arsenic safe throughout the country, might get depleted because of the vertical mobilization of arsenic. I did a modeling work of that to look at the kind of time frame as well as groundwater recharge pathways through to modeling in the southeast part of Bangladesh, where the area which is highly contaminated with arsenic. There is also salinity, high salinity concentration in groundwater as well. And in the modeling work, we consider a number of different aquifers. We considered all kinds of obstruction from domestic irrigation to very deep municipal water supply system, and we put everything into the model. And then we also did the particle tracking analysis to see where the water was coming from. And our modeling work actually suggested that uh, if the current stratification of different pumping, so the domestic water supply coming from shallow, irrigation water supply coming from the intermediate level of the aquifers around 70, 80 meters, and then some municipal water supply coming from at a depth of around 150, 200 meters. If we have this business as usual kind of scenario going forward, then we projected that with the pumping increase in 2050, even at the end of the century, we will not have arsenic going into the deep groundwater because the time it will take more than 100 years or more. That's through the simulation work. But we also model that if everything now comes from the deep, so the shallow irrigation as well as domestic water supply, everything comes from the deeper aquifer, then the time frame reduces and you tend to see the breakthrough of arsenic from the shallow to the deeper system within a matter of few decades.
Right,
So
right.
we recommended that the deep groundwater has to be preserved for the foreseeable future only for drinking water supply, because this is the only remaining source of arsenic and salinity safe drinking water source in Bangladesh. So we must protect it. And I think there is a big consensus within the kind of research communities, as well policymakers, as well as government. Um, uh, they are actively trying to protect that deep groundwater resource.
Right. And you mentioned the contaminant levels of arsenic, the World Health Organization with 10 micrograms per liter and Bangladesh with 50 micrograms per liter. In the US, our regulations changed in the mid 2000s from 50 micrograms per liter down to 10 micrograms per liter, then a lot of community water systems and public water supply systems became non-compliant, and so now there's a lot of water treatment to address that issue, but we still have a lot of systems that have arsenic issues, and so that reduction in the maximum contaminant level in the US created problems and is still being addressed. And I guess as part of your work with your institute, IRDR, you're also looking at other health impacts of salinity in groundwater. Maybe you can briefly describe the impacts of high salinity in the coastal zone on health effects.
Yes, yeah, definitely. Because I sit in an interdisciplinary department, I often work with epidemiologists and even medical doctors, particularly to look at impact of contaminated water on people's health. So I have been involved in a research funded by the Wellcome Trust a few years ago, where we looked at health impact of drinking high salinity groundwater. And we know that from research as well as publications that came out in this topic, suggesting that there is a very strong correlation between hypertension, so high blood pressure, and the exposure to high drinking salinity contaminated drinking water. And in the coastal area, aquifers are mostly contaminated with high salinity. So when I say high, we are talking about 1500 plus microsiemens per centimeter of electrical conductivity, or EC, or nearly 1,000 milligrams per liter of TDS, total dissolved solids. So it's very high concentration of salt that is affecting particularly pregnant women. So during the kind of second to third trimester in pregnancy, women can develop high blood pressure, and that can lead to a health outcome called preeclampsia, and that is quite dangerous for the mother and their unborn child or children. So there is very strong kind of association between salinity contamination and health, and I'm very interested in that topic.
It's a fantastic opportunity for you to work with epidemiologists and medical people, because most of us don't interact with those groups. So, and to make those linkages between water quality and health, I think it's fantastic. Maybe you can describe a little bit, because some of the listeners may not be familiar with the history of Bangladesh. I was looking up, you have a population of about 170 million people, and you mentioned earlier that maybe 20 of those in Dhaka, in the capital. So how does the history, I mean, I know India is influenced a lot by the British, and you know, they switched from surface water to groundwater, but it seemed like you followed a parallel trajectory, even though you had a different colonial history. So maybe some of the things you know, you experienced some similar things to India in terms of hydrogeology, even though you had a different colonial history.
I thought we had the same colonial history, isn't it? The whole of Indian subcontinent was ruled by the British Empire for nearly 200 years. So we have a very strong history of colonial past, and we are part of the British Commonwealth right now, and so we do share similar history, if you like. So yeah, in terms of course, when it comes to groundwater development in particular, I think we are in a better situation because the whole of Bangladesh is part of the Ganges, Brahmaputra, Meghna Delta system. We have very highly productive aquifers. We hardly have any areas that is covered by the hard rock. We have some advantages here in terms of the kind of development of our water resources. And I think that has been a blessing for Bangladesh in many ways, because if you imagine a country that is as big as the state of I think is it Atlanta or sorry, the state of um, is it Georgia? Yeah, so or the state of perhaps Alabama, where I studied some time ago. Uh, we have a population of 170 million, so it's a huge population we're talking about. Uh, and but we are self kind of reliant in terms of our food supply and water supply. Bangladesh has come a long way in the last 50 years since the independence in 1971. People don't necessarily die because of hunger these days. At least we don't hear in the news that we used to hear 20, 30 years ago. So I think in the whole uh, the in the whole sort of food security area, we have achieved quite a lot. And I think being a hydrogeologist, of course, I'm biased, but I think I would I would not hesitate to say that the contribution to the food and water security in Bangladesh has been possible because of the abundance groundwater that is situated in the country.
Right. So when I was talking to my husband last night and trying to describe what we had discussed recently, Shams, and he said, well, Bangladesh was under Pakistan rule from the late 40s to the early 70s. And so when you had this transition from surface water to groundwater, you weren't, you differed, your colonial history differed from India, but you still had that shift from surface water to groundwater. So that's kind of what I was talking about.
Yeah, no, that this is quite interesting. That actually some of the infrastructure that we have in Bangladesh in terms of monitoring of surface water as well as groundwater, those infrastructure was actually established during the kind of late British colonial period, and then passing on to the Pakistan government. So we were part of the East Pakistan until 1971 when we became an independent nation.
Right, right. So it's a very interesting. It's wonderful that you can do so much work in Bangladesh, even though you're now living in the UK and everything, but that you can contribute to understanding the water issues and the food security. And you mentioned food security. I mean, I think now they grew up to 3 different crops of rice a year. And so that is a huge plus in terms of food security. And that's facilitated by groundwater irrigation during the dry season. So that has been a huge plus. So,
That's
but
correct.
you've also, you mentioned much of the work that you've talked to as far as now has focused on groundwater wells and monitoring those water levels and trying to understand what is happening in the system. But you also use remote sensing quite a bit in your work.
Yes, I do.
And
I love mapping, and I love being a remote sensing person as well. So
it's
yes, I
it's
did
such a
use a lot of.
such a wealth of information that we have to look at, and I think you started off in the late 2000s when Matt Rodell and others at NASA were talking about the depletion that the grey satellites was showing in northwest India, and you also looked at the grey satellite in Bangladesh. Maybe you can describe some of the results of that work.
Yes, yes. So yes, I was inspired indeed by that Nature publication led by Matt in 2009. And at the same similar, I think in a similar time frame, there was another paper by Tiwari, also using GRACE satellite data reporting groundwater depletion in India, and I think they also included Bangladesh in one of their study areas. And that got me thinking that, okay, so I think they reported something like 4 cubic kilometer per year of depletion was taking place at the time when I was doing my PhD, and I got the whole monitoring data from Bangladesh Water Development Board. So I thought, okay, why don't I maybe test the grace signal for the Bengal basin using my observational data from groundwater as well as surface water levels that I was able to process. Lucky, I mean, unfortunately, we don't have a very good network of monitoring soil moisture in Bangladesh. So for that, I had to rely on some of the large global models that are available through the GALDAS, the GLDAS global data assimilation system, I think. So when I looked at the data, I used number of different GRACE products off the shelf. I'm not a geodesist, so I don't necessarily process the primary GRACE data. So I looked at published GRACE signals from different sensors. And actually, I found very interesting correlation between the GRACE-derived estimate of groundwater storage change versus observation data-derived groundwater storage change uh, for the Bengal Basin of Bangladesh. And we also depleted, I mean, we reported depletion of groundwater if we consider the whole of the basin and in the order of, I think, less than 1 cubic kilometer per year. That compared very well with GRACE-derived estimate of groundwater storage. So I thought overall we had a good validation of GRACE data using in situ monitoring.
And what you mentioned there is important, that the GRACE monitors total water storage from the atmosphere to the deep subsurface, but then trying to figure out where that storage is changing, if it's surface water, soil moisture, or groundwater. And so some of your results also emphasized the importance of groundwater storage variability. I think that accounted for maybe 30% of the storage variations that you saw.
Yes, yes, you're right. You're correct. So GRACE TWS gives us an overall picture of what is happening in the soil zone, in the surface water system, as well as in the groundwater. So in the work that I led in the Bengal Basin, suggested that the kind of compartmentalization of different, storage uh, uh, using observation data suggested that surface water was actually representing nearly 33% of the overall GRACE TWS signal. Similarly, I think soil moisture as well as groundwater, both of the different signals were sharing similar proportion of variability that we see in the TWS. So I think for the first time, when we published that paper in Water Resources Research Journal back in 2012, we reported a huge contribution of surface water variability to the estimation of groundwater from GRACE signal. And I think I haven't actually seen many publications using GRACE data to go to that extent and report contribution of different components to the overall variability. So I thought it was quite an interesting piece of work.
Right, right. And I mean, total water storage is very valuable in its own right. And now the global climate observing community recognizes total water storage as an essential climate variable. So I think that's very valuable. But then trying to figure out where the storage changes are occurring is very important if we want to manage these issues. And you followed up that work then in Bangladesh with a global analysis of aquifers. And I thought that was a really nice study, because you provide all of the data. You provide the total water storage, you provide all of the different components for the major aquifers globally, and the time series and everything. So people can look at all of the data and try to understand what's going on. And I think one of the big conclusions from that study is that there's a lot of interannual variability, whereas previously we emphasized, long-term trends and just linear trends. But your analysis suggests that, it goes up and down at different times in response to dry periods or wet cycles or things like that. So maybe you can describe that a little bit, Shams.
Sure, yes, yes. Yes, so of course, by the success of the kind of validation work that we did in the Bengal Basin um, after my PhD, so I thought, okay, maybe we can look at the global scale what is happening. And of course, I was inspired very much by your work. you looked at spatiotemporal dynamics in TWS, so the total water storage in the large river basins around the world. So I thought, okay, so let's maybe go one step further and try to estimate groundwater storage change for 37 large or the mega aquifer systems around the world, using a number of different GRACE products, again, using off-the-shelf published GRACE datasets. And I use large, land surface models data to get surface water, soil moisture, and ice and snow water storage. And what we found in that study is that, as you just mentioned, that the seasonality component in many systems was the dominant system compared to the long-term trend. And the trend, of course, you can fit a linear regression to a time series and report a trend, either it's a depletion or rising trend, but that doesn't actually tell you the interannual variability or the impact of seasonal variation in the data set. So we concluded in that paper that we published in Earth System Dynamics journal that the nonlinear signal of groundwater storage from TWS was quite dominant. Great. So I think I was talking about the nonlinear behavior of groundwater in the large aquifer systems, and I think that was quite fascinating finding, because if you just fit a linear trend and report spatiotemporal trend variability in the aquifer on a map, you necessarily don't see how perhaps the interannual variability in the time series are impacted by extreme rainfall events. So that was a discovery that we have seen in a number of different aquifers, particularly in the semi-arid and primarily in semi-arid to subhumid systems, including the Central Valley, California, where I think you have done a lot of work in the past, that we have seen sudden rises in the estimated groundwater storage. And when we looked at the rainfall data, we could see that heavy rainfall or years with very high amount of rainfall actually contributed to the reversal of the signal, depleted signal, and then recovery was happening in those aquifers. And you can see that we have seen it in a number of different aquifers, and we thought it's a very interesting finding, because that has something to do with how we define resilience or sustainability. Because if you think about a system being linear or behaving as a linear system, you don't necessarily going to define your sustainability in a robust manner that I think we were able to do in that global scale analysis.
Yeah, I think that was very interesting. And I mean, some of the points that you make, the seasonal signal is dominant. It's maybe accounts for maybe 60 or 70% of the GRACE signal, but the trends, then the long-term trends can maybe be less than 10% of the signal. But most of the emphasis in the past has been on those long-term trends. And understanding, the declines and the recovery is very important. I mean, in the Central Valley, we do get some recovery during wet periods, maybe with reduced pumpage, increased surface water use. But over the long term, over the past several decades, there's been a general decline, because the recovery is never enough to bring it back to what it was pre that dry period. So this understanding is very helpful. So I guess we're getting towards the end of the time period discussing these things. I'd like to ask you, Shams, you have contributed a lot to hydrogeology in Bangladesh, and I was wondering, what are your thoughts for the future of water management and food security in that region?
Yeah, that's a very, very good question, and thank you for asking it. I think what this Bengal Water Machine paper in particular did, that um, it really put groundwater um, in the picture. Because often in Bangladesh, because groundwater is everywhere, we take it for granted. We don't necessarily think, that the important role that this particular natural resource has been playing in terms of addressing food security or water supplies, and also going forward, we are talking about climate crisis, uh, and how much climate change is going to impact in the future, going forward on our water resources. So I think um, uh, this this paper and my long-term contribution to the science of groundwater in Bangladesh will create a lot of awareness, not only among the member of public, but also within the policymakers and the government sphere, that we should be recognizing the importance of groundwater, but at the same time, we will be looking at the potential of these groundwater resources that can be further exploited sustainably. Of course, in the areas where we have seen the Bengal Water Machine operating, perhaps these are the areas where we can see the potential of further developing. But at the same time, we have to be quite cautious where the depletion is taking place. So there has to be a balance found. And I think going forward, we should be using both surface water as well as groundwater conjunctively to address the long-term kind of sustainability and food security issues, not only for Bangladesh, but I think the region as a whole, because I'm quite interested in the Asian mega deltas, and they all share similar kind of uh, um, geology as well as socioeconomic dynamics. So I'm an optimist. I think uh, we can address challenges that are posed by climate change and also human development as a whole.
And I really admire your work, Shams, and what you have, the understanding that you have brought in looking at groundwater level data and remote sensing information in Bangladesh and other regions globally. I mean, Bangladesh is the fourth largest producer of rice in the world, I think, and a lot of that is facilitated by groundwater irrigation, and then doing that in a sustainable, using sustainable practices will be very important. And so improving food security and how it has improved food security in the past decades is very valuable. You published your first papers on these groundwater level data in 2009. It takes a long time to bring these concepts and ideas together and to understand the system, and then to get people to read the work and to assimilate the results, and then bring it into to decision makers and policy makers and impact those. So great job, and it's wonderful that you can contribute so much to Bangladesh. You grew up in Bangladesh, and your family is still, your mother and your siblings still live there. So it's great that you can contribute so much back to their water resources and food security. Thank you so much for doing this podcast with me. I've learned a lot in talking with you and really appreciate collaborating with you. Hope you have a good evening.
Yes, thank you so much, Bridget. It's always pleasure talking to you. I have learned so much from you, and I'm looking forward to further collaboration with you in the future. So thank you very much again for having me on your podcast show,
Okay.
and wish you all the best.